Welcome to the debate. Today we're digging into something pretty foundational in C++ object design. The whole meaning and enforcement of the const keyword. It's really one of the language's core safety promises, right? A guarantee about data integrity.
Right, but as soon as you start using it as a C++ practitioner, you immediately hit this fork in the road. You've got these two, well, competing ideas. There's the compiler's very literal guarantee, what we're calling Bitwise Constness, which is all about the physical memory, the actual bits. And then there's the, let's say, abstract intent of the person designing the class, Logical Constness.
Exactly. And, that split really sets up our central question for today. From a practical standpoint, where should our priority lie? Do we stick rigidly to that very strict physical safety promise of bitwise constness? Or do we need to use tools like the mutable keyword to achieve this higher level idea, logical constness, which, lets us do sophisticated things like caching or thread safety, even if, it adds some complexity to the implementation.
And I'll be arguing that, well, to really maximize safety and keep implementation risks low, we have to prioritize that strong default guarantee of bitwise constants. We should really trust the compiler here as our most vigilant guardian of data integrity.
And I'm going to argue that prioritizing logical constants isn't just, nice to have, it's actually essential. It's pretty much the only way we can build robust, high-performance APIs that genuinely uphold the semantic contract that the client expects when they're holding a const object. So my core position here is that logical constness is, well, fundamentally the only workable model if you're aiming for high-quality, efficient C++ code. Why? Because it respects the public interface contract. When someone, a client, calls a function on an instance they know is const, their expectation, reasonably, is that the observable state isn't going to change. What we might be doing under the hood, internally, especially if it involves, say, metastate or performance tweaks that really ought to be invisible to them. Think about Memoization, for instance. If you've got a getter function that's computationally heavy, maybe it's calculating the sum of squares for a huge data set, you definitely don't want to rerun that whole calculation every single time the function gets called. We need to cache that result somewhere. Similarly, when you look at thread synchronization using something like Mutable, std mutex, that's what makes sure logically non-mutating functions can still be called on const objects, even in a multi-threaded program. The mutable keyword, it's explicitly there. It's the safe, language-approved way to separate these internal, often performance-related details from the core observable data. And that's what lets us build performant thread-safe APIs.
Okay, yeah, I understand the drive for efficiency and for clean APIs. I really do. But the main benefit, the core win of const correctness, is letting the compiler enforce a very clear physical constraint. Bitwise constants is the default for a reason. It's simple, it's unambiguous, it guarantees that the actual sequence of bits making up that object in memory, they won't be altered by a const marked function. And in big, complex systems, that kind of structural guarantee is frankly priceless. So when we introduce mutable lie, we're deliberately poking a hole in that absolute guarantee. We're essentially saying, okay, compiler, you can relax here. And we're shifting the responsibility for correctness from that static check back onto the individual programmer. Now, even if the intention is purely optimization, the fact is you are modifying internal bits. That weakens the guarantee, and it demands, intense discipline from the programmer. You mentioned caching. Well, now you need robust cache invalidation logic every time some non-const function updates the underlying data. That's a complex, manual task, and it's a common place for bugs to creep in. Bitwise constness, just by its nature, eliminates that whole category of problems by default.
But we have to look at the practical reality, right? What practitioners actually face. If we completely rule out using mutable for modifying internal, non-observable state, well, the only other option, and it's a dangerous one, is that constcast t this hack. And mutable is just inherently better. It's safe, its behavior is well defined by the standard, and it provides explicit documentation of your intent right there in the class definition, where implementation details belong. Using constcast to try and achieve logical constness, that's a huge red flag. And the reason it's so risky is Undefined Behavior, UB. And this isn't just some theoretical concern. If the object itself was actually declared const somewhere else, like const t my object, then its data might physically live in read-only memory. The OS might even enforce that. So any attempt to modify it through that cast pointer could just crash your program with a segmentation fault. That's exactly the kind of catastrophic runtime failure C++ safety features are meant to prevent. Mutable, on the other hand, it's a declarative tool. It respects the language rules. The compiler knows how to handle it safely.
Okay, I absolutely agree that constcast is, well, it's basically a sign of desperation. It should be avoided, no question. But the very fact that you need mutable seems to highlight a kind of conceptual conflict here. You're basically arguing that because one unsafe escape hatch exists, constcast, we should embrace a slightly safer escape hatch, mutable. But my point is, Bitwise Constness, done right, eliminates the need for any escape hatch. When you rely just on the const t type for the this pointer inside a const method, there's no complex runtime reasoning needed. It just maintains that pristine memory state, the clarity, the absolute nature of that bitwise contract. For many development teams, that's worth sacrificing some convenience, maybe some internal optimization. It forces a cleaner separation. If a function needs to modify any state, even internal state, well, maybe it just shouldn't be callable on a const reference in the first place. Let's pivot to that thread synchronization point you raised. That's definitely a strong argument for mutable, I'll grant you. But think about what's actually happening when you use mutable mutex. Locking and unlocking a mutex, that fundamentally modifies its physical state. Its internal bits change to reflect whether it's locked or not. So aren't you kind of sacrificing conceptual purity, the idea of no modification, just for implementation convenience?
Well, I think that line of reasoning misses a really crucial distinction, the one between the core object state and, let's call it, administrative metastate. Look, without mutable stead.mutex, functions that are logically read-only, maybe something like connection status const, they'd have to be marked non-const, simply because they need to grab a quick lock internally, maybe just to safely read an atomic variable. And if you force connection status to be non-const, you're sending the wrong message to the client. You're telling them that calling this function might actually change the connection itself, which is semantically just false. It also means clients can't even call that simple status function if all they have is a const reference to the networking object. That severely limits the API's usefulness. You have to think of the mutex not as part of the object's persistent data, but more like the key to the room where the data lives. The client only cares about what's in the room, the connection status. The fact that we're turning the key, modifying the mutex's state, that's just administrative overhead. It's about thread scheduling, not the object's fundamental observable state. And mutable correctly models that necessary separation.
But that conceptual distinction, doesn't that open the door to misuse? Where do you actually draw the line? Okay, today it's a mutex, fine. Tomorrow, maybe it's some internal performance counter that tracks how many times a function is called. If your function is physically modifying memory bits, even if you label them metastate bits, declaring that function caused kind of misrepresents the physical reality of what's happening, doesn't it? We're trading the rigor of a simple universal rule for a much more subjective, designer-defined rule.
The line, I think, is drawn by the observable contract with the client. If that counter you mentioned is purely internal, never exposed, then modifying it under the protection of const is generally acceptable, provided it's done in a thread-safe way, of course. If, however, that counter is user observable, maybe there's a public get call count method, then yeah, modifying it probably needs a non-const function, or at least its observable effect has to be considered part of the non-const operation. That's just the necessary professional scrutiny a class designer has to apply. Let's circle back to caching for a second, because that's where the need for performance really intersects sharply with constness. When we use mutable for things like lazy initialization or caching results, the modification is typically very controlled. We're usually altering only a redundant copy, the mcache members say, not the core immutable data like mdata. And doing this is often essential for highly performant APIs, right? So the core responsibility then naturally shifts to the non-const mutator methods. When a client changes the core data, maybe through a non-const setter function, Well, that setter must handle the necessary cache invalidation. It has to say call mcache.reset or something similar. And look, that requirement, that's just a standard part of the job description for writing professional performance C++ code. It's the price you pay for optimization.
But see, that's exactly it. You're shifting the safety check entirely away from the compiler's static analysis and putting it squarely on the programmer's shoulders, relying on their manual runtime logic. And that manual step, well, that's precisely the weakest link in the argument for Mutable in these cases. You're essentially trading the risk of undefined behavior from Const, which, okay, we both agree is catastrophic, for the risk of stale data. And stale data is often a silent, insidious logic error. Think about maintenance, right? In a large team, maybe 6 months down the line, some new developer adds a new setter, maybe update data v2, but they forget or they don't realize they need to implement the cache invalidation logic. The compiler won't say a word. The code builds perfectly fine. But now, your application might start returning stale, incorrect results from that cached getter. And those bugs, they are incredibly hard to track down because the error isn't immediate. It's temporal. It depends on missing manual code. The beautiful simplicity of Bitwise Constness just avoids that entire class of subtle bugs altogether. By forbidding the alteration of the cache within a const method in the first place, it forces the computation to happen when it's requested, reliably.
Yeah, okay, I see why you emphasize that risk. But that argument almost sounds like we should avoid necessary complexity just because developers might make mistakes. We are practitioners, and often, performance is a critical feature. If the cost of getting that high performance is needing to manually implement cache invalidation logic correctly, then, well, that's a cost we often have to accept. And besides, modern C++ gives us pretty robust tools, things like stu.optional or carefully managed state flags to handle cache validity much more reliably than just simple reset calls. The design has to clearly separate the core state from the derived cache state. And if you do that correctly, the safety you gain by completely avoiding constcast, plus the performance benefits from caching, I think they far outweigh the added manageable complexity.
But why even expose yourself to that category of risk if you don't absolutely have to? If the object's logic is genuinely complex, maybe Bitwise Constness forces a cleaner design up front anyway. Perhaps it pushes you towards making the computation function external, or using a function object that captures the necessary data by value or const reference, instead of relying on internal mutable state within the const method itself. Every time we lean on Mutable just for optimization, we create this implementation-dependent artifact that kind of breaks the simple, clean principle of immutability that const is supposed to represent.
That's needed for the operation, and honestly, making a const object effectively unusable because its key operations are too slow without internal caching, that's also a failure of API design. If I hand my client a const reference to my, say, high-performance geometry engine, and they discover they can't call calculate surface normals because I forgot to mark the internal cache, or maybe a synchronization primitive, Mutable, I've fundamentally broken the contract with them. They expect a read-only operation like that to be callable on a const object.
That's a fair point about the client's expectations, definitely. But perhaps the issue lies in defining the contract around external convenience rather than focusing first on internal state integrity.
Yeah, I think at the end of the day, this whole debate really centers on how we define the semantic contract in C++. My view is that const has to be seen as a promise to the client, primarily about observable state and behavior. And Mutable, it's the idiomatic, safe tool C++ gives us to implement that promise efficiently, enabling really essential techniques like lazy initialization and robust thread safety. We absolutely should default to const by default in our designs, but then use Mutable deliberately, thoughtfully, where high performance or thread safety genuinely demands it.
And while I concede that Mutable is sometimes necessary, especially for managing metastate like Mutex is for synchronization, the practitioner really must always remember. Bitwise Constness provides that default highest baseline of safety that's actually enforced by the compiler. Every single use of Mutable is an exception to that strong safety guarantee. It demands intense scrutiny, clear justification. Sticking to the strict interpretation arguably forces clearer initial class designs because it makes all modifications, even purely internal ones, explicitly non-const, unless you have a very compelling reason related to non-observable mechanisms to use mutable.
So the practitioner finds themselves needing to balance, really, balancing the rigorous, unambiguous safety you get from the physical memory guarantee of Bitwise Constness against the flexibility, the performance gains that come from defining this higher-level logical contract. That feels like a central C++ trade-off, doesn't it?
It really does. Choosing between that simple, absolute safety and the potential for sophisticated, high-performance flexibility requires careful judgment. And the consequences of that choice, well, they ripple through all stages of a project, from the initial design right through to long-term maintenance and evolution. There's certainly more to unpack there.